record this. Let me take attendance. Oh, there we are. So Guess is theoretically sleeping, although there's a decent chance she's working on her college applications, but I'm not going to judge. I'm actually quite proud of myself, Sophie, that it's only Tuesday and that they're not due till Sunday, but I'm all done with Sophie's letter and it's turned in. No, it's okay. It's okay, but it's like, no, I'm done. All right. So we're going to talk a little bit about what I like to call hidden forces. Okay, so your book calls them common forces, which probably works as well. But I think of them as hidden forces because they're forces that they don't tell you about in the problem. They're forces that they assume that you are going to know are there. Okay, and things that you are supposed to remember. So the first one, of course, is going to be, that should be a star, and it's not, is the gravitational force. So I have never seen a problem in which it starts with the Earth pulled on the box with a gravitational force of 50 newtons, okay? They may tell you that the mass of the box is 5 kilograms. They may tell you the weight of the box is 50 newtons, okay? But they're not going to come right out and tell you about that force. So it's your job to remember that that force belongs in the free body diagram, okay? So we kind of talked about this a little bit yesterday, but if I have an object that's going to be in free fall, then what's the only force that's acting on that object? Right, the gravitational force. Okay, so the only force that's going to be acting on there is going to be Fg. And remember that that Fg force always points towards the center of the Earth. Whether you let that be up or down is another story. Okay, I'm sorry, whether you let that be positive or negative is another story. It's always down. And we'll remember that as we make some different kinds of free body diagrams. Okay. So remember that this Fg, this gravitational force, is also going to be equal to and sometimes referred to as the weight of an object. Okay. And did they give you a formula for Fg in the book? What is it? mg. Okay. And we'll talk about where that comes from after we learn about Newton's second law. Okay. And we're actually going to, after we do the other things I want to do today, we're actually going to try to, I have some spring scales that will give us some Fgs. I have some masses that will give us some Ms. And we will try to figure out what G is another way. I don't know if it'll work. I didn't want to touch everything. I washed my hands before I put it all in the box, but we'll see what happens. Okay. All right, so another hidden force is the normal force. Sometimes the normal force is called the support force. And it's called a support force because this is basically the force that keeps the pen from falling through the table. Okay. So if I have some kind of table or surface, and I have a box on there, that table is going to exert a force that we call N. Sometimes I usually call it N. Some books will call it F sub N. It may come up that way in a problem or in something that you read. Please remember that this N is not newtons, okay? It's not the unit, it is a force. And we may refer to it just as capital N if we're talking about its magnitude. So it's called a normal force because normal means what? It's an old-fashioned word for what? Perpendicular, okay? So it's always going to be perpendicular to the interface. So if I have an object that is on an incline, then that normal force is perpendicular to the incline. And I think we had at least one problem example like that in the free body diagram videos, okay? All right, we're good. So what's the third force that they talked about in the common forces section? Tension, okay? Now, tension is the force that we get when we've got a cord or a rope or a string or a chain that is connected to an object and is pulling it. That's kind of the easy way to deal with it. Sometimes what we have are two objects that are connected by a rope, and we'll do some examples like this. And the important thing to remember here is that the tension is always along the rope, okay? And that the tension force always goes away from the object, so that when we're drawing the free body diagram, the tension force always points going away from the object. It's also important to note that a rope only has one tension. That means that I didn't just label both of those tensions in my picture T because I'm lazy. I did it because they actually have the same magnitude, they just point in opposite directions. Okay. We will also encounter pulleys, but as far as we are concerned, a pulley just changes the direction of the tension. Okay, that will change several chapters from now, but we're not going to worry about that. For right now, we will consider all of our cords and strings to be massless and unstretchable, so that we don't have to worry about the cord as an object itself. Again, that's something we'll deal with later. But right now, it's just a way to connect those two objects. Okay. So it's worth noting that not every problem will have all three of these hidden forces. If there's no rope or chain or cord, there's not going to be a tension force. Okay. If the object is a cord that's hanging from the ceiling with a ball on the end that the wind is blowing, there's not going to be a normal force. There won't be a normal force unless our object is resting against something. Annabelle. If it were hanging, no, because it's not touching anything. It's not resting against anything. Okay, so that's a really important thing to remember, is that just because there are three of these forces doesn't mean that all three of these forces are going to be in every problem that you solve. And that's an issue that comes up often in students, okay? So your book keeps dancing around friction and mentioning it, but that's really going to be in the next chapter where we will really look at that, okay? So I think that the next thing that I would like you to do is, do I have that? Oh dear, where is it? Is it in here? I don't think it is. Did I lose it? Maybe it's under stuff to remember. I think it is. Not that you should go to stuff to remember, but I guess you need to. Okay, so if you go to our forces tab under our OneNote notebook, there's that tab called Stuff to Remember. You don't necessarily have to download that because that was just for me because I found this really cool interactive and I didn't want to lose it. But if you click on it, the first one, okay, you should get something that looks like this, okay? And if you go down, there's this interactive that says free body diagrams. Okay, is everybody there? Okay. And you can click on this arrow in the upper left corner and it'll open it up and make it big. And then you can click on start at the bottom and it gives you 12 situations. We are not ready to do all 12 yet, but you can do 3, 5, 9, and 11. I'll put it in the chat for you so that you know what the numbers are. 3, 5, whoops, 3, 5, 9, 11. Okay. So try real quick to do those. See if you can get yourself 4 stars. When you click on it, it has, let's hang on a sec. Let me get rid of this thing at the top. It gives you a scenario. So this says a rightward moving car is skidding to a stop across a level roadway with its wheels locked. Ignore air resistance. So for instance, we all know that gravity is going to be part of this. So if I want to include gravity, what direction does gravity point? Down. So I would click here where it says down. And it gives me a choice of forces. So I'm going to choose gravity. Okay, and you can change the magnitude of the force by clicking on it. There's really only 2 choices, but it helps you determine whether something is bigger or smaller. Okay, and you should indicate that. So go ahead and work on that for a couple minutes. And then we'll see if we need to go over any of them. I just need to move around. How are we doing? How many have you done? 3? Are you done? Okay, who's done? Just Tia. Okay, that's cool. Okay, well, we can go over any of them together. Dagny, how you doing? How many you got done?
I have 2 done.
Okay.
I'm working on the 3rd one.
How we doing? Anybody stuck? Yeah, we're stuck. Okay. Which one are you stuck on? Number 5. Okay, so let's look at number 5. So number 5 says a rightward force is applied to a crate to push it across the floor at constant speed. Ignore air resistance. You are, oh, okay. Oh, good. Oh my gosh, did they change? Oh. Crumb. Because I picked the 3, I picked 4 that you could do. This one? That's Flutter Nutter. Oh, that really annoys me. What was your number 5? It probably only has a normal force and a gravitational force, because there wouldn't be any friction. No, because it's snow. Probably not. Oh, okay. Oh, cool. Because what did it say? Did it say it was slowing down? Okay, then yes, then there is friction going the opposite. Okay, I'm really sorry. I tried to pick a bunch. I did, like I went through and I picked the 4 that didn't have friction because we haven't done friction yet. Okay, never mind. We'll just come back and do this whole thing when we've done friction. Oh, that's so annoying. Okay, so let's go with another way to calculate G. We've got 21 minutes. We can do it. Okay, so we just discovered that a formula that we can use to calculate the acceleration or to calculate the force due to gravity or the weight is mg. And what I have in my newly cleaned hands okay, what I have are a bunch of spring scales. And the white scale on the spring scale is newtons. Okay. And what I also have are a whole bunch of masses. And if you put the mass on the spring scale, you can move this on the spring scale. So we have masses and we have forces. So what's going to be our independent variable? Remember, the independent variable is the one that you choose, the one that you could change. Mass, okay? So what will our dependent variable be? It's not a spring constant. It measures what? It measures the force, actually, which will be Fg, okay? We could figure out the spring constant, but that would be a completely different thing, okay? So if we have these two things and we put a bunch of masses on there and we measure a bunch of FGs or a bunch of forces, how are we going to calculate G, little g? No, because that only takes one data point into consideration. What's the best way to do something? You're going to do multiple masses. We're going to pool all of our data together, and then what? No. So you've got F is equal to mg, or maybe gm would be a better way of looking at it. What do we usually call our independent variable? X. What do we usually call our dependent variable? So if I've got y equals something times x, it's a line. You take the slope of the line, and what will the slope of the line be? G. Okay. So a graph is a really great way to take all of the data into consideration, because when you make a graph and you plot your data points, are you going to play connect the dots? No. You're going to make a trend line. You're going to make your best fit line so that some of your points are above and some of your points are below. So if something wacky happens, like Eva talks to Annabelle when she's making a reading and she messes something up, that point is going to be way far out. And you're going to know that it shouldn't be a part of your trend line. Whereas if all you did was take a whole bunch of F's and divide them by a whole bunch of N's, you're going to have this wacky value that you're going to average in, and it's going to change things. So a graph is an excellent way to kind of weight your data appropriately. Okay, so once again, I'm going to wash my hands. So make a data table, and then Tia, transfer your data table to make a page in the collaboration section. There may already be a page there. Just wash my hands. Okay. No. I have no idea. Figure maybe how many of you are there? 6. So figure at least 18. Everybody's going to be 3. Okay. So I'm just going to give out masses. Some of these you might end up with similar masses. Some of them might not like work very well. We'll see. What's yours? Okay, try to make as many different combinations as you can. If you have a mass hook, you can maybe do a little bit more with it. Okay. Oh, most of the ones like this have a hook in the bottom, so you can actually hook them together, okay, and combine them. So see how many different combinations you can make. If the spring scale goes down below 5 newtons, you're not making an accurate measurement, okay? So the other thing to note is that many of these are all in terms of grams, and you want them to be in kilograms or your units won't turn out right. Okay, so make sure you convert them, put them in, and then we'll see what happens. Collaboration space. Group lab data table. Is that what it is? You can make your own and then put it in there. I would actually, I'm going to change this data table. Oh wait, no, maybe this is what I wanted. Excellent, perfect. I just didn't have that in there. Okay, so put your data in there. Take it yourself, put it in. If we get multiple value, if different students measure the same masses, that's okay. We'll average those values together, or actually we can put them all in the data table. You don't go above 500 grams. And that's what'll happen is it won't read anymore. Oh, it's probably just the spring being stretched out. Oh yeah, do your best. You could trust, sure. What I'm concerned is that it's not going to be linear, which means that the more because springs aren't necessarily linear, that the more I stretch it, it's going to be a different amount that it's off by. But try it. Try correcting for that. Let's see what happens.
Dr. Goetz,
Yes, Dagny.
could you just explain how we have to calculate G from this? I just couldn't hear that.
Sure. So what we're going to do is, because the mass is our independent variable, you're going to plot that on the x-axis, okay? And then Fg, or the force, is what you're measuring. So that's going to go on the y-axis. So if we have, which we do, Fg, and I'm just going to write it this way for the moment, Fg is equal to Gm. This is my y, is equal to my slope times my x, right?
Mm-hmm.
So we're going to plot all our data points. This is going to be m. This is going to be Fg. It should be a straight line. And then the slope of that line should be little g.
Okay, thank you so much.
Sure, no problem. I was afraid when I was standing far away, and I was afraid you weren't.
I could hear it. It was just sometimes it would come in and out. But I think that's because of my Wi-Fi. So.
Well, it could have been me too. So I'm glad you asked. I'm sorry you can't participate in the activity, but you can get the data. And make sure, Fiona, you got to turn it around. You have to read the white side. The black letters are the, okay, but make sure you're reading the correct. Make sure you are reading the side that is in newtons, not the side that is in grams. It's okay, it happens. If we were able to do the Atwood's machine lab, which we probably won't be able to do, you end up with all these masses on this pulley thing. And what happens, because it's what always happens, is it goes too fast and the mass hits the pulley and everything goes everywhere every time. I hate that noise. It happens. It would probably give you, no, because it would also have the weight of the, or the mass of the spring slot of this, like the whole container in there. But yes. Mm-hmm. It should be. It needs to be kilograms or the units won't work out right. You can change it if you like, Fiona. I think it was created before I made that point. Yes. You probably should. Yes, but I worry that it's not a linear shift and that I would imagine it would be less than that when you have a larger mass on there. But but it makes sense to do that. I'm not entirely sure it's gonna make sense.
I was thinking if they all start, if 0.3 is kind of the starting point for all of them, would it matter if we subtracted because the slope is still be the same?
But I don't know if it's the same for everybody's spring scale. And like my spring scale, sometimes it's at 0.3, but sometimes it's at 0.2. So what we need is a new set of spring scales, but I didn't even realize some of them were broken. And the thing is I'm afraid that when you put more mass on there, it's not gonna be off by the same amount because springs aren't necessarily linear. Which means that the amount you stretch it doesn't, like in a linear spring, if I stretched it twice as much, the force would be twice as much. In a nonlinear spring, if I stretch it twice as much, the force might be twice as much. It might be less, it might be more. So well, I'd like you to do it with all the data. So yes. So that's like what you need to do before you come to class tomorrow is you need to add your data into here, okay, into the collaboration space. And then the first thing we'll do in class tomorrow is we'll plot it and see what we come up with. And then we'll do the Newton's second law, exploration. And then we probably won't start Newton's second law until Monday. I think I did change it so that the 5.3 was for Monday. Okay, because I was looking at it and it just seems like that's because we don't have class on Thursday, so we're losing a whole class period plus flex, and then Friday's our drop day. So sure, try it. Yeah, if you had a spring scale that needed to be adjusted.
Is homework 2 still due Friday?
That's a really good question, Dagny. Let's see what homework 2 is. Oh no, because it's Newton's second law. So no.
Okay.
Yeah. No, you can't do that. You should be able to do, yeah, you should be able to do homework 1 still. When was that due, or is that?
That's due tomorrow.
Yeah, homework 1 is still due tomorrow. I'll adjust homework 2.
Okay, I just want to make sure. Thank you.
Sure. Oh. Because what? Sure. Oh God, I forgot about that. We have a pumpkin, and I've refrained from saying, so all 6 of us are going to touch one pumpkin. Huh? I chose not to be obnoxious. Anything you got? Like maybe ribbon and glue and... Oh, no, because we're in the chapel, so we are definitely not going paint. I don't think, I meant to email you guys and I forgot. Paint marker, I think paint markers we could do. But I'm thinking more stuff we can glue on and glue. Yeah. I thought maybe we could like go swoop in and out, but it was like, because one year everybody got their own pumpkin, right? Yeah, but it was like, whatever. Okay, so just leave everything and I will collect all that stuff and spray it. And then, but please put your data into, oh, and a lot of it's there, okay? And we'll plot and do that stuff tomorrow, okay? Yeah, because I'll collect it and then you guys don't have to hover in front of the box and breathe on each other and all those terrible things. Okay, bye guys, see you tomorrow. Probably the whole freezing part.
Golf team to the front hallway. Crew team on the white box.